Today I'm going to be discussing limits. So first let's consider the standard notation. So if I wrote down the following, where f of x is a function, then the following statement reads as follows, that the limit of the function f of x as x approaches a is L. Right, so graphically what that amounts to, what this looks like is as follows. So if this is a on the x-axis, then as x approaches a, and we can approach a from the left hand side and from the right hand side, meaning from values less than a, so we call that below a, and for values bigger than a, so we call that above a. So as we approach a from both sides, observe how we approach the values associated to the image of the function. So you then observe that if this was L, then as x approaches a, we have that f of x approaches the value L, and that is precisely what is summarized in this notation, that the limit of f of x as x approaches a is L. Right, so here is an example which I would like to just tackle in both ways, both graphically as I had described it to you here, as well as just investigate it algebraically. So let's consider this. We now want to calculate the limit of the function h of x as x approaches 2, where h of x is a split function. So it is a function given by x squared when x is not 2, so that means we will draw x squared and then exclude the coordinate associated with x equals to 2. And it will then be equal to 1 when x is 2. Now recall from the notation that you've learned previously. Since x is being excluded, we shall denote that coordinate by an uncolored dot. And since x equals 2 in this step is included, we then denote that coordinate by a solid dot. So what is the coordinate associated with this open or uncolored dot? So at x equals to 2, what is the associated y value in this rule? So if I plug in 2 in here, I then observe that I get a y value of 4. In the second rule, if I plug in x equals to 2, what is y? It is fixed at 1. So when we now draw these coordinates on the xy plane, we shall now use the notation that I've just established here according to these dots. So let me put down these dots, these coordinates immediately. So at 2 and 4, I'm now going to have that open dot, and at 2 and 1, I'm now going to have a solid dot. So those coordinates have now been plotted. So I've already taken care of the coordinate associated with the second rule. I just now have to plot everything from the first rule. I have to draw x squared and ensure that that point is the open dot which I've already put in there. So let's draw x squared. That's just the parabola, the basic parabola. So let me draw the first half here, and then that continues. So observe that everywhere on this line there are continuous solid dots, but here I kind of skip a point and then I continue with the solid line. And then let me draw the rest here. Okay, I'm not sure if it was done perfectly, but here is a parabola that is drawn and it satisfies rule 1. So it has been drawn for all points except at 2. So observe, I would have drawn, I'd come to this point, stopped, picked up my pen, and then drawn again. I would have picked up my pen because I would have to jump down here to color it in, then jump back up to continue with the rest of the parabola. So this is a split function resulting in this graph. Right, so let's now inspect what is happening. We want the limit as x approaches 2. So I need to approach 2 from the left and the right. So when I approach 2 from the left and the right graphically, what do I observe? So observe as we approach 2 from the left, we are now approaching that y value, the image is 4. And similarly, as I approach 2 from above, I observe that I'm still approaching that y value, which is 4. So observe that graphically the limit as x approaches 2 of h of x is equals to 4, because both from below and above we've arrived at the same value of 4. Alright, so now let's compute this algebraically. Right, so in order to do this, you now need to make use of your properties of limits, which was included in your notes, so please make sure that you read it. Right, so in here we are now computing the limit as x approaches 2. So we're not investigating what happens at x equals to 2, we are investigating what happens around x equals to 2. And as a result of that, when evaluating the split function, the rule that satisfies what's happening close to x equals to 2 is the first rule. So that's the one that I'm working with. So the limit as x approaches 2 of h of x is actually just going to be the limit as x approaches 2 of x squared. X squared is a polynomial. By the properties of limits that we have learnt, you can simply substitute in your value of x into that, so that becomes 2 squared, which equals to 4. So both graphically and algebraically we have obtained the same limit value. Right, so this should now start to sort of make sense to you as to what is happening. But I want you to observe something, and this is the reason why I've chosen this example in particular. Whilst the limit of h of x as x approaches 2 is 4, observe that h of 2 is not 4. What is h of 2? Where is x equals to 2 defined? It's defined in the second rule, and it's been assigned a value of 1. So this is what I want to say, that the limit as x approaches 2 of h of x is not equal to h at 2. So keep that in mind. You will come across these really nice properties as you proceed to learn more about limits. Right, next example. Compute the following limit. The limit as h approaches 0 of f of x plus h minus f of x divided by h. And we are given that f of x is equal to x squared plus 1. So observe, in order to calculate that, we need to obtain what is f of x plus h. So all you'd have to do here is replace x by x plus h. So let me do that. So since that's x, if I replace it by x plus h, it becomes x plus h squared, being added to 1. And then if I simplify, square the binomial, that's x squared plus 2xh plus h squared plus 1. So f of x plus h is now equal to that. So putting everything into this formulae, the limit as h approaches 0 is now equal to f of x plus h, and that is what I have, x squared plus 2xh plus h squared plus 1 minus f of x, and f of x is x squared plus 1 divided by h. Now, using our properties of limits, you would think that since this is a quotient, you could then distribute your limit into the numerator and into the denominator immediately. But observe that the denominator would then be evaluated as 0. So because of that, we cannot use that property which I have just mentioned. Instead, we would have to proceed by aiming to simplify what I've written in the square bracket and then evaluate the limit. So let's simplify. So if I simplify, I've got x squared plus 2 times xh plus h squared plus 1 minus x squared minus 1 divided by h. Now observe that we have terms cancel off, so x squared minus x squared, positive 1 minus 1. So I'm now left with the limit as h approaches 0 of 2xh plus h squared divided by h. Once again, observe in this quotient, I still cannot employ that limit property of distributing it into the numerator and denominator. So I still need to simplify. So now observe in the numerator, I can factor out h, and I'm left with 2x plus h divided by h. So those cancel, and now I'm left with the limit as h approaches 0 of 2x plus h. And now observe that at this point in the problem, we can now distribute that limit in. And so what we then have is This then becomes the limit of 2x as h approaches 0 plus the limit of h as h approaches 0. Since this is a limit regarding h, 2x is actually regarded as a constant and it remains unchanged. So we're just left with 2x. And here, h can be regarded as a polynomial, and you're substituting h equals to 0, so that is just 0. So the final answer is 2x.